Okay, let's get started. As I said, I'm going to go low level, building on what we did last time. But the reason I want to talk about this is actually to emphasize something else, which is the importance of building infrastructure and research. So research actually, research takes time, as I said, right? The impact takes time. Sometimes it happens after your lifetime and you never know about it. If it happens earlier, that's good, of course. So you can see your ideas getting some impact in real systems, right? But doing research itself also takes time, right? If you remember this picture that I showed you from the RowHammer lecture last time, we built this infrastructure, and this particular picture is actually from the infrastructure from 2011 that we built. And the goal was to actually study the retention areas. I'm going to talk about retention today. And this infrastructure, as I mentioned earlier, Ataberk just recently released a paper on the updated version of this infrastructure. And we built this infrastructure in 2011 and open sourced in 2017. And our goal was to study something called data retention, as I mentioned last time. And I'm going to talk about that because it's very fundamental and interesting. And you can see this an updated version of the infrastructure in 2014. You cannot see the bottom of the slide for some reason. Are you sure there's no way to get rid of that? Can you try double? Can I try double? Anyway, you can try while I'm talking. It's a terrible interface, right? Zoom interface.
But people will be able to see everything. Or maybe not.
Oh, that's fine, I think. No, even worse. Yeah. Maybe you go back. Maybe you go to full screen. Maybe that was not full screen.
This was full screen.
Why do they have that stuff in the full screen? Height.
It's health. Well, you don't see yourselves.
Yeah, that doesn't work.
Right there.
Okay, anyway, maybe there is no easy way. I guess on live stream you're okay. It's just this picture, this whatever gets projected over here. Okay, so this is where we did a lot of RowHammer experiments, and this is when we released it. We made it actually much easier to use. This is part of Hassan's thesis, PhD thesis. It's flexible. It's easy to use. It's even more easier to use right now with DRAM Blender because it's Python API, right? And open source. And this has enabled a lot of studies, like RowHammer studies, as we discussed, right? Some studies that were previously not possible to do. But the reason we built it is because of this. What does this look like? I keep seeing these all over already. This is a liquid DRAM cell. No. Oh, here my That's a real demonstration of leakage, I would say. It's a waste, right? Where does that water go? I actually recently taken another one, but I couldn't find it on my phone. It's all over the place. It's such a big waste, in my opinion. Like, look at that. Like, I tend to notice these things and see how much waste there is in the design of, in general, the macro things around us. We do try to optimize a lot in the micro level, but there's a lot of waste we eliminate also. But this is the kind of waste we're trying to eliminate, basically. Oh, I don't know what happened. It's moving again. So I mentioned this paper last time. We wrote this paper. How many people know about this paper? Okay, some people do, probably. It's fine. How do you know about it? Probably the lecture.
No, from the course.
Okay, yeah. I actually covered this more. Oh, in computer architecture. Yes, definitely. We covered a lot more in the computer architecture. So some of this is going to be boring for you because you've seen it earlier. If you're taking computer architecture, I mentioned this also in digital design and computer architecture, but we don't go into a lot of detail. But we basically wanted to eliminate refresh. That was our goal as much as possible. And this is the paper that, and basically we proposed some ideas over here. I'm going to actually mention them. And then these ideas were in simulation, and we believe that these ideas are good actually. And then we wrote this paper saying that actually you can get rid of a lot of refresh. I'm going to mention this briefly. And then the question is, can you actually really make it happen? So that's the reason why we built this infrastructure. Can we get rid of refresh? And we've been building this infrastructure since 2011. And that's what I'm going to talk about this paper. In fact, I'm going to give a presentation of the paper that I gave in ISCA 2013, 10 years ago. My student couldn't present it, but I presented, and hopefully it'll be interesting. It's this paper. So let's talk about it. Does that sound good? It's like a real conference presentation, of course, in a different setting. I'd be talking, let's say, much more methodically in the ISCA conference talk. Okay, so DRAM refresh, for example, I could have used that example if I had that picture in the talk, but I didn't have that picture at that time. So a DRAM cell, you've seen this also last week, consists of a capacitor and an access transistor. It stores data in terms of charge in the capacitor, and essentially this charge leaks. And a DRAM chip consists of tens of thousands of such rows of cells. So it's big, basically, and it's becoming bigger. And the problem is DRAM capacitor charge leaks over time. As a result, each DRAM row is periodically refreshed to restore the charge. This is called a refresh. In other words, you activate each row every n milliseconds, and typical n at the time was 64 milliseconds. Today we're at 32 milliseconds and lower at higher temperatures. So there are many downsides to the refresh. It consumes energy. Each refresh consumes energy. This is kind of the waste of water we've seen, right? We're wasting energy. And DRAM rank or bank are unavailable while the chip is being refreshed. There's a quality of service impact. You get pause time during refresh, and refresh rate actually limits DRAM capacity scale. So this is what we argued in the earlier paper in 2012. I'm going to use those slides. I borrowed those slides from that paper. You cannot see it referenced at the bottom. Really annoying. Thanks, Zoom. So the paper is referenced at the bottom behind that Zoom thing. So basically, this shows that as you increase the capacity of the DRAM device, the percentage of time you spend refreshing increases based on some modeling and expectation, of course, right? So why does this happen? Because there are two reasons. First, in a device that is higher capacity, you have more rows. So you have more rows to refresh. And second, as you go to higher capacity, cells become leakier because cells become smaller. So there's a lot of noise in the cells. As a result, you need to refresh every cell more frequently. Because of this double effect, the amount of time you spend refreshing a 64 gigabit DRAM chip that's what we suggested, is about, let's say, 46% of the time. You can think of this as throughput loss of the DRAM chip. 46% of the throughput of the DRAM chip is gone. You just need to refresh. You can also think about it as the water that you cannot use in that thing that I showed you earlier, right? The fire hydrant. You have a solution? No? Okay. Okay. And the energy is very similar. Basically, as device capacity increases, and you can see present, we had 8 gigabit capacity devices. Today, we have 16 gigabit capacity devices, maybe 24 also. But basically, we're marching towards from the left to the right. And we expected that the energy spent on accessing DRAM will mostly be spent on a refresh. Yeah, this is the percentage DRAM energy spent refresh with some access probability, etc. So this depends on how frequently access DRAM. So for example, as I said last time, the thing in my pocket is refreshing its memory right now. It's wasting energy. I'm not accessing it. If I'm accessing it, clearly that fraction would be lower because this is a fraction of the total DRAM energy that's spent. Okay, but we motivate this as an important problem. And there's work that observed that there's significant variation in the data retention time of DRAM cells due to manufacturing process variation. And retention time is defined as the maximum time a cell can go without being refreshed while maintaining its stored data. And these prior works propose methods to take advantage of widely varying retention times among DRAM rows. So, for example, the work that we presented at ISCA the previous year to this paper reduces the refresh rate for rows that can retain data for longer than 64 milliseconds. And you can actually, assuming that you can identify them. There's earlier work actually that shows that disables rows that had low retention times. That was in 2006, as you can see. And there's a bunch of other work that we referenced in the paper. And these works all show large benefits in energy and performance. So let me describe the work that we did last year. Well, when I was presenting, it was last year. Now it's 11 years ago. So basically, RADAR, retention over intelligent DRAM refresh, it consists of 3 steps. You first profile the retention time of all DRAM rows. And then you store the rows into bins by retention time in the memory controller. Basically, you categorize the retention types. And we use Bloom filters for efficient and scalable storage. So basically, you categorize retention time over the entire DRAM like this. And the distribution looks like this. and you store the addresses of rows that need to be refreshed frequently into Bloom filters, which provides scalable and efficient storage. And we showed in the earlier paper that you need only 1.25 kilobyte storage in the memory controller for a 32 gigabyte DRAM memory. So it could be very efficient, basically. And then the memory controller uses this information, the Bloom filters, to refresh rows in different bins at different rates. So that's the promise. And this work showed that you can reduce refreshes by 75%. And this reduces energy consumption and improves performance, as shown by that work and other works also. Makes sense, right? Okay. So the problem is this work and all of the other works require accurate profiling of DRAM row retention times. So that's what we're targeting in this work. To maintain data integrity while reducing refreshes, we need to have an accurate and reliable measurement of retention time of every single DRAM row. And the assumption is that worst case retention time of each row can be determined and stays the same at a given temperature. That's what these previous works assumed. For example, some works, both of the works that I mentioned from 2006 and 2012, propose writing all ones and zeros to a row and measuring the time before data gets corrupted. That's your retention time. Now, the question, of course, the scientific question is, can we actually do this? Can we reliably and accurately determine retention times of all DRAM rows? And that's what this paper is all about. So there are two challenges that make this difficult. And one is data pattern dependence, and the other is variable retention time. Let's take a look at these one by one. Data pattern dependence says that retention time of a DRAM cell depends on its value and the values of the cells nearby it. Why? Because things are too close to each other and things are coupled. Let's take a look at that. So when you activate a row in DRAM, all of the bit lines that are connected to that row are perturbed simultaneously. So let's take a look at this pictorially. So you have a row that's called a word line, another row over here, and these are the bit lines, and these are the cells hanging off of this word line, meaning the row. So if you activate that row, this blue thing over here, word line, the blue bit lines over here get perturbed simultaneously because what happens is the capacitors over here get connected to the bit lines and all of those wires get perturbed. And there's electrical noise on the bit line. And this electrical noise affects the reliable sensing of a DRAM cell along that row. And the magnitude of this noise is affected by the values of the nearby cells. Let's take a look at that. So there's bit line to bit line coupling. So if you're reading the cell over here, there's coupling that happens due to the perturbation that happens when you read simultaneously the cells that are connected to the adjacent bit lines. And there's bit line to word line coupling. If you're reading the cell, there's electrical coupling between the bit line and the word line that's activated. And this coupling actually affects the retention time as well as the values you may read. Okay, so basically, because of this coupling, you affect the data that's stored in other cells, and the retention time of a cell depends on data patterns stored in nearby cells. And if you really want to find the worst case retention time of a cell, you need to find the worst data pattern. Otherwise, you may actually get some retention time that's not the worst case. And this is going to pose a challenge, as we will see. The second challenge is maybe even harder. We call this this is called the variable retention time. And this is the phenomenon that retention time of a DRAM cell changes randomly over time. A cell basically alternates between multiple different retention time states. And this is reported in literature as early as 1987. Basically, the leakage current of a cell, leakage current that goes from the capacitor to the transistor to the bit line, sporadically changes due to a trap in the gate oxide of the DRAM cell access transistor. And this trap happens, and randomly this trap becomes occupied. And whenever this trap becomes occupied, charge leaks more readily from the transistor's drain, and that leads to a short retention time. Basically, you can think of this with the picture I showed you. That fire hydrant, once in a while, dumps a lot of water. And this happens randomly. Okay, this is called trap-assistant GIDL, gate-induced drain leakage. And previous work in electron devices conferences showed that this is a random process. Basically, the takeaway is that worst case retention time of a cell depends on a random process. Can we easily determine the worst case given this fact? Okay, so our goal in this work is to basically understand these effects, To do so, we would like to analyze the retention time behavior of DRAM cells in modern commodity DRAM devices so that we can aid the collection of accurate profile information. And we provide a comprehensive empirical investigation of two key challenges to retention time profiling, which I introduced: data pattern dependence and variable retention time. So this is what I will talk about next. Basically, we built an infrastructure to characterize DRAM. I'm going to talk about that and then provide some foundational results to validate that infrastructure. And then we're going to talk about the data pattern dependence and variable retention time issues and talk about our conclusions, which basically will be there's more future work needed. So we developed this DDR3 DRAM testing platform using Xilinx FPGAs. It's temperature controlled. We tested more than 200 commodity DRAM chips from 5 different manufacturers. And there's 7 different families of chips based on equal capacity per device. You can see we're going to look at these later on. And basically, each experiment consists of multiple rounds of tests. We do this round of tests to ensure statistical significance of the test, because one random test you may get a result, but then if you do it many, many times, those results average out, or you can actually find outliers. And each test essentially searches for the set of cells with a retention time that's less than a threshold value for a particular data pattern. This is a mouthful. So let's take a look at a high-level structure. Basically, we write a data pattern to rows in a DRAM bank. We prevent refresh for a period of time called T-wait. We leave the DRAM idle during that time. And then we read the stored data pattern, compare it to the written pattern, and record the corrupt cells as those with a retention time that are less than T-wait. Basically, some cells get corrupt after T-wait idleness. We are going to assume that that's because of a retention error. Again, this is an assumption. This is one of the limitations of the study. This may not be due to a retention error. It may be another error mechanism, but we repeat this test many times. So there's some statistical significance to it. Okay, so there's test details and important issues to pay attention to are discussed in the paper. You need to be careful, basically, how you design these experiments. So this is an example experiment structure. This is round 1, round 2. What we do is we start testing the bank, and then you write the data pattern X to the bank and wait for 1.5 seconds. And this tests both the data pattern and its complement. And then, of course, read basically whatever I said, you read and check for corrupt cells. And then you do write data pattern Y and then data pattern Z. And then we do another data pattern X, but now we increment the waiting time to 1.6 seconds. So this way we go from 1.5 seconds to 6.0 seconds at some temperature, as we will discuss later. So that's considered a round. This way you collect for all data patterns and for all potential retention times, all the corrupt cells that you see. And then you repeat this experiment for statistical significance. So you can do thousands of runs of testing. So in our tests, most of our tests are conducted at 45 degrees Celsius, and we don't observe any cells that have retention time less than 1.5 seconds at 45 degrees Celsius. And we test T-wait in increments of 128 milliseconds from 1.5 to 6.1 seconds. So this is a lot of tests, a lot of experiments, basically. Let's take a look at tested data patterns, because it's going to be important for data pattern dependence demonstration. Basically, as previous work suggested, you can write all zeros and all ones to all of the bits. Previous work suggests that this is sufficient. But we also test checkerboard patterns, consecutive bits alternate between 0 and 1. And the reason we test is because this increases coupling noise, because this causes more voltage difference between the neighboring bit lines. And it may induce worst case data pattern if adjacent bits are mapped to adjacent cells. Now, that's not necessarily true, but this increases the probability that we test such things. So we also have a walk pattern, which attempts to ensure that a single cell storing 1 is surrounded by cells storing 0 to maximize the coupling. This may lead to even worse coupling due to coupling between nearby bit lines, as prior work also showed. And we permute the walk pattern in each round to exercise different cells, and the paper discusses that permutation. And then there's random testing. Basically, randomly generated data is written to each row in this case, and a new set of random data is generated for each round. Basically, this covers cases that we cannot cover with fixed patterns clearly. So these are fixed patterns. Walk is actually also not a fixed pattern, but it's a methodical change. Random is completely random. Okay, so let's talk about how we validate this infrastructure. By the way, in hindsight, we should have shown the picture of the infrastructure in the talk, but hindsight is always 100%. Yeah. So certainly we need to keep temperature stable, and we have a temperature. We have a let's say bare bones temperature controller for this, and basically this shows our validation. And over time, you see that there's some error margin in the temperature, but mostly we can keep it stable at different levels. And we can test chips at 5 different stable temperatures, as you can see. And then we also repeat some of the foundational results that prior work showed to validate the goodness of our infrastructure, let's say. And this is a bit more involved. Basically, we analyze the dependence of retention time on temperature, and prior work reported very clearly there is a strong dependence of retention time on temperature, and our results actually agree with prior work. Let's take a look at this, what we did. Basically, this temperature on the x-axis and normalized retention time on the y-axis. So this normalized retention time contains a fraction of cells that exhibited retention time failure at any T weight value for any data pattern at 50 degrees Celsius. So you can see that all cells are over here right now, right? Because that's normalized. Every cell should be there. Now, the next data points or data point distribution over here shows the normalized retention time of the same cells at 55 degrees Celsius. So you can see that the retention time is reducing, and there's a distribution that's happening. Some cells are, let's say, for some cells, retention time is reducing less. For some cells, retention time is reducing more. And you repeat this until we get to 70 degrees Celsius. So we have normalized retention time of the same cells. The cells that were failing over here, same cells. How is the retention time distribution over here? Now, and then we have best fit exponential curves for the peak and the tail. Peak meaning the most populated part of the distribution, as you can see, this densest part of the distribution, and the tail is the lowest possible retention time cells. And we fit these curves, and basically we validate our, we see the same relationship previous work has seen. Relationship between retention time and temperature is consistently bounded, predictable within a device. And every 10 degrees temperature increase leads to a 46.5% reduction in retention time in the worst case. Okay. So we also do another validation, which is the retention time distribution over here. Our minimum tested retention time is 1.5 seconds at 45 degrees Celsius, which corresponds to about 126 milliseconds at 85 degrees Celsius. And this actually agrees with prior work. Today's at 85 degrees Celsius, the refresh rates are 32 milliseconds. So we actually, this shows that there's some margin in the retention times. And very few cells exhibit the lowest retention times. And the shape of the curve is consistent with prior works. Prior works have actually shown this curve. And we also observe, unfortunately, you cannot see it, but newer device families have more weak cells than older ones. This is likely a result of technology scaling at the bottom. It's not seen in this, whatever here, but it's seen over there. So this is likely a result of the technology scaling. So let's take a look at this basically. So this is an older generation. You can see the retention time distribution looks like this. This is on the x-axis. On the y-axis, you see fraction of cells with a retention time that's less than the x-axis value. So if this fraction is higher, there are more cells that are failing at a given retention time, at a given x-axis value. So this is older. This is a newer generation from manufacturer D. You can see that more cells are failing in the newer generation at the given retention time. So this is a result of technology scaling, we believe. Cells are smaller and there are more cells, more rows. So another one. An older chip over here from manufacturer A, a newer chip from manufacturer A, you can see that the retention times are becoming worse. More cells fail. Okay, so those are our foundational results to validate our infrastructure. Previous work has shown this. Now let's take a look at some new results. And we're going to look at data pattern dependence first. So let me set some terminology first. We're going to look at failure populations. Basically, a failure population of cells with retention time X. This refers to the set of all cells that exhibit retention failure in any test with any data pattern at that retention time. And that retention time is indicated as T weight. And then this is actually a failure population of all data patterns. But then we also want to analyze a specific data pattern. We define the term retention failure coverage of a data pattern DP. This is the fraction of cells with retention time X that exhibit retention failure with that particular data pattern. Okay? Divided by the failure population that I defined earlier. So if retention times are not dependent on data patterns stored in the cells, we would expect coverage of any data pattern to be 100%. Basically, any data pattern should be able to discover any cell that's failing. Right? Basically, if one data pattern causes a retention failure, any other data pattern should also cause a retention failure. So let's take a look at recall the tested data patterns. These are the data patterns that we're going to test. I'm going to show you results with that. So basically, we don't see that. We basically see widely varying retention failure coverages for different data patterns. This is an example from manufacturer A's 2 gigabit chip family, 6.1 second retention time. That's what we test basically, and 45 degrees Celsius, as I mentioned. And you can see the number of rounds over here. The fixed patterns, it doesn't matter what round you test, the coverage is the same because you don't change the pattern with the rounds. Whereas the dynamic patterns, you can see the walk pattern and the random pattern, their coverage keeps increasing. Maybe there are some asymptotes, we don't know. But the rounds are, these are a lot of rounds actually. You said you test the chip after 16 rounds. So basically the takeaway here is that different data patterns have widely different coverage. Data pattern dependence exists and is severe. And coverage of fixed patterns is low. For example, if you tested all zeros and ones as prior work suggested, you get only 30% coverage for retention failures, which is not good. And walk is the most effective data pattern for this device, but you can see that even that is not 100% coverage after 16 rounds of testing, expensive testing based. And this is one device. No data pattern achieves 100% coverage rates. But you cannot see that, unfortunately. That's right under the Zoom's beautiful interface. Yes.
Did you figure out what 100% is?
Okay, let's go back to the definition. I defined it. So basically 100% is the failure population of cells with a retention time. It's the set of all cells that exhibit retention failure in any test with any data pattern for that given T weight. Basically, whatever we tested. It's not the ground truth because there's something else probably that we didn't test that. If you want to really get the ground truth, you should test all possible data patterns, which is impossible to do in a lifetime. That's a lot of data patterns, a lot of combinations, right? We're talking about billions of cells in a chip. Okay, but that's a very good question. We define it. Okay, so another chip from B this time, 2 gigabit chip family. Random is the most effective pattern for this device. So you cannot use the same pattern across devices. Random, again, it doesn't get to 100%, but it gets close. But you can see that other patterns are pretty bad, let's say. And another chip from C, manufacturer C. Here, random happens to be also better, but it doesn't get, it gets even worse than close to 100%. Okay, so basically our observations are similar across devices, across chips, across manufacturers. So we believe these are fundamental. So basically, a cell's, let's summarize the observations. A cell's retention time is heavily influenced by data patterns stored in other cells that we have empirically shown. Pattern affects the coupling nodes, which affects cell leakage. And no tested data pattern exercises the worst case retention time for all cells. In other words, no pattern has 100% coverage. In other words, no pattern is able to induce the worst case coupling noise for every cell that we've seen. And we see one problem over here. And the problem is that underlying DRAM circuit organization is not known to the memory controller. In other words, from our perspective, as non-manufacturers of DRAM, it's very hard to construct a pattern that exercises the worst case cell leakage. So we believe that this is a fundamental problem. And also, there's another issue that exacerbates this, which is the opaque mapping of addresses to physical DRAM geometry. We don't know exactly which bit we write gets physically adjacent to which other bit, because there's some mapping, internal mapping that goes on, and we don't know that. Later works actually reverse engineered a lot of that, but that's later than this work. So the reason first of all, the mapping is opaque, and there's also internal remapping that goes on internally in the DRAM chips to tolerate faults. And again, we don't know that. So what we think is adjacent may actually not be adjacent inside the chip. As a result, we may not be able to design a data pattern that has the best coupling. There are other issues that we don't discuss actually in this presentation, like true and anti-cells, but the paper discusses that. So basically, also one more thing that makes this difficult is second order coupling effects are very hard to determine. The first order, maybe we can capture, assuming we kind of ignore the two, but then there are second order coupling effects that happen in the circuits, and those are very hard to determine. So we also see that fixed and simple data patterns have low coverage, as I've shown you. They do not exercise the worst case coupling noise. And the effectiveness of each data pattern varies significantly between DRAM devices of the same or different vendors. So this indicates that underlying DRAM circuit organization likely differs between different devices, which means that patterns leading to worst case coupling are different in different devices, as I've also shown you. So that's not so good. Basically, you cannot take one pattern and use it for every device. And we've also seen that technology scaling appears to increase the impact of data pattern dependence. And the reason for this is scaling meaning when you reduce the size of the circuit elements, capacitor, for example, you reduce the physical distance between the circuit elements, and this increases the magnitude of coupling effects. Okay, so let's take a look at this. Actually, I have not shown you this one, but I will show you now. These two figures, comparing these two figures, show the effect of technology scaling as an example from a manufacturer A. So if you look at this chip family over here, the lowest coverage data pattern achieves much lower coverage for the smaller technology. So a checkerboard, for example, lower coverage, all zeros and ones, it achieves much lower coverage. Actually, all of the patterns achieve lower coverage as you go from one technology node to another technology node. And we have similar examples in the paper for other manufacturers as well. Yeah, but I mean, if you look at the lowest coverage, checkerboard going is lowest here, all zeros and ones over here, you clearly have a jump. Okay, so basically, what are the implications of this? We have a lot of results, more in the paper, and there are some implications that we draw. And the first implication is that if you are trying to get rid of refreshes with some retention time profiling mechanism, you have to handle data pattern dependence of retention time. Intuitively, you can identify the data pattern that induces the worst case retention time for a particular cell or device. But there are two problems. One, it's very hard to know at the memory control which bits actually interfere with each other due to opaque mapping of addresses that I mentioned earlier. Logically consecutive bits may not be physically consecutive. And remapping of faulty bit lines and word lines to redundant ones internally within the DRAM exacerbates this problem. And the second problem is worst case coupling noise is affected by non-obvious second order bitline coupling effects that are very hard to let's say reason about easily. So we suggest some avenues for future work. A mechanism for identifying worst case data patterns likely requires support from the DRAM device. And we believe DRAM manufacturers might be in a better position to do this. However, the ability of the manufacturer to actually identify these cells and expose the entire retention time profile is limited by what I'm going to discuss next, which is variable retention time. So manufacturers are not in the best position for this. An alternative approach, which could be more promising, is to use random data patterns to increase coverage as much as possible and handle incorrect retention time estimates with ECC. So if you somehow incorrectly identify a retention time, hopefully you'll have enough error correcting codes. And these are relatively random errors as we have seen. So error correcting codes could be a good option for this. But of course, to be able to do this, you need to keep profiling time in check, because random data patterns, as I showed you earlier, it may take 16 or more rounds to get to even 90% coverage. For ECC to be productive, you need to actually do the calculations, and you really need coverage more than 98% or so. Okay, so you need to keep ECC overhead in check also. So there's a trade-off over here between how much profiling you do and how much error correcting codes you use. So actually, this was a slide that was on target. Let's say there's a lot of work that happened after this that looked at profiling versus ECC overheads, including some of our work. Okay, so in hindsight, you can see actually how things evolve. Let's talk about the second effect, which is variable retention time. We're going to do some analysis on this. So remember that this was the phenomenon that retention time of a cell can vary over time. And remember that because a cell can randomly switch between multiple leakage current states due to trap-assisted gate-induced drain leakage, which appears to be a random process. And this was first discovered in 1987 in this paper by Yanni. And Russell actually has a lot of interesting data on it. You can see that these are IEDM, electron devices meeting papers. Okay, so this is an example of a VRT cell we actually observe in our system that we test. This is a cell from manufacturer E's 2 gigabit chip family. You can see that y-axis is time and y-axis is the retention time of the cell. Maximum retention time we test 6.1, minimum is supposed to be 1.5, let's say. But you can see that the cell's retention time is not constant. In many cases, maximum time, basically the cell retains data for 6.1 seconds, but there are many cases also where you have a dip in the retention time. So that shows that there's some variable retention time effect that's happening. So we want to answer multiple key questions. First, how prevalent is variable retention time in modern DRAM devices? What is the time scale of observation of the lowest retention time state? Basically, how long do we need to test to get to the lowest retention time state? And can we be sure about it? Can we be sure that we're actually getting to the lowest retention time state? What are the implications of retention time profile? So for this, we test each device for at least 1,024 rounds over 24 hours. Many rounds right now. Temperature is fixed at 45 degrees Celsius. And data pattern used is the most effective data pattern that we discovered for each device in the prior testing for data pattern. And for each cell that fails at any retention time, we record the minimum and the maximum retention time that we observe. So let's take a look at that. Let's summarize for a particular chip family from manufacturer A. So on the x-axis, we see the minimum retention time. On the y-axis, we see the maximum retention time. And this is the population of cells that basically we plot the density, population of the cells that fall into a particular XY point, minimum and maximum retention time. And if the minimum retention time of a cell is the same as the maximum retention time cell, well, if there's no variable retention time, we would expect every single failing cell to fall into this line, x equals y line, because minimum retention time should be the same as maximum retention time. But we see almost exactly the opposite. Most cells, you can see, are over here. This population density is higher over here. And most cells are actually over here. So basically, most failing cells, most cells where we observe retention time failures exhibit variable retention time. Their minimum retention time varies widely compared to the maximum retention time. And you can see that there are many failing cells that jump from very high retention time, which is 6.1, to very low, which is 1.5. This is 45 degrees Celsius. So basically, variable retention time phenomenon is real. This is B's 2 gigabit chip family, same thing. C is a very similar thing. So you see some very similar pictures for all manufacturers. So let's take a look at our observations so far. So variable retention time is common among weak cells, meaning those cells that experience low retention times. And variable retention time can result in significant retention time changes, as we have seen. The difference between minimum and maximum retention times of a cell can be more than 4x and may not be bounded because we cannot do infinite amount of testing. So we don't know in the end, but we observe 4x. And the implication is that finding a retention time for a cell and using a guard band to ensure minimum retention time is covered requires a very large guard band or may not go. I mean, if you interpret this in a different way, you set the retention time of a cell and you basically add some guard band saying that this is, I actually protect for the worst case, but you may not know the worst case because you don't know what's the minimum retention time unless you do infinite testing. So basically, that's the problem. The retention time profiling mechanism must identify the lowest retention time in the presence of this variable process, variable retention time. The question is, how long do you need to profile a cell to find the lowest retention time state? So we tried to answer this question also, meaning we basically wanted to see the time between retention time state changes. How much time does a cell spend in a high retention state before switching to the minimum observed retention time state? And this is real data from A's 2 gigabit chip family. You can see the time spent in high retention state can be very large. And this is the relative frequency of the amount of time that's spent based on our rounds of testing. So for example, here, the chip spends time in the high retention state for 4 hours before switching to the low retention time state. So you need to test the chip for 4 hours at least. But that's not enough, clearly, because there are cases where sometimes 1 day is spent on the high retention time state before the cell switches to the low retention time state. So the testing cost of really finding the lowest retention time of a cell, we believe, is unbounded currently. Okay, so I've already said this. No, you can see that one, that's good. So basically, you need to profile for a long time to get to the minimum retention time state. And this picture is very similar for different manufacturers. This is B, this is C. You can see very similar pictures, as you can see. So what are the implications on profiling mechanisms? Basically, the first problem we see is that there does not seem to be a way of determining if a cell exhibits variable retention time without actually observing a cell exhibiting variable retention time. This seems to be a true random process, and we don't know how to model it or predict it. The second problem is it's actually very difficult for the DRAM manufacturers to identify the retention time profiling. We cannot punt to the DRAM manufacturer in this particular case, like we did in the DRAM data pattern dependence. Because once you solder DRAM chips to a board, for example, you either a DIMM or directly to a board if you do in the LPDDR, for example, you expose it to very high temperatures. And this can induce VRT in cells that were not previously susceptible. Basically, the VRT profile changes due to exposure to high temperatures due to soldering. For example, soldering. As a result, if manufacturer determined via, let's say, extensive testing for some with their knowledge of the circuit, which is also very hard, which we believe, their retention time profile may not be accurate. So one option for future work is very similar to what we have just discussed earlier for DPD. We believe you can use error correcting codes to continuously profile DRAM online while aggressively reducing refresh rates. And error correcting codes can handle the cases where you get a retention error because you thought that your minimum retention time was actually higher. But of course, you need to keep ECC overhead in check if you want to do this. Okay, so that brings me to the end. So to summarize, DRAM refresh is a critical challenge in scaling DRAM technology efficiently to higher capacities and smaller feature sizes. And understanding the retention time of modern DRAM devices can enable old or new methods to reduce the impact of refresh. And many mechanisms that were proposed and probably will be proposed in the future require accurate and reliable retention time profiles. We presented the first work that comprehensively examines the data retention behavior in modern commodity DRAM devices. We characterized more than 200 devices from 5 different manufacturers. And our key findings show that retention time of a cell significantly depends on data patterns stored in other cells. We call this data pattern dependence, and changes over time via random process variable retention time. We discussed the underlying reasons and provided suggestions. And we strongly believe that future research on retention time profiling should solve the challenges posed by the DPD, data pattern dependence and variable retention time phenomena. And that concludes the talk. Now, this was 10 years ago. You can see that this was motivated by the idea over here. Can we do this? And this paper says, oh, maybe not. At least not now. So it's very important to do this in research, basically. Research moves on ideas, right? I think it was really important to write this paper to tell this idea that no one, let's say, thought about before. One option could have been, okay, we don't write this paper, basically we say, okay, we write the second paper. But, I mean, there may be use cases for this idea that you may not think about also, right? So there's actually a tendency of when do you actually decide when to expose research, right? So we decided, even while we were doing these studies, we decided that it was important to expose this idea without any data from real chips, based on what was discussed prior in research. And that had some contribution clear. But then, of course, we want to make it real. So we actually design this infrastructure and we do the studies. And okay, maybe this idea is not that easy to implement. Then the question becomes, of course, how do you make it happen? And that's why later works came. This is some of our works. There are other people who actually also done works. This paper, for example, looks at how do you actually look at different techniques, error correcting codes, profiling, online profiling, etc. What are their effects on DRAM retention pairs? This looks at variable retention times even more, for example. There's a lot more data over here. And again, this paper is not fully conclusive as well. It proposed online profiling using ECC in a little bit more, but it doesn't provide a completely, let's say, error-proof or bulletproof methodology, but a lot of data, a lot of interesting data. This paper shows that you can actually do what we suggested in a more robust way. You can actually cover for variable retention time errors using error correcting codes by online profiling. I'm not going to talk about that. So this is a reasonably robust mechanism. And this paper looks at data dependence failures. Basically, can we identify which bits are affecting which other ones in the underlying DRAM chips? What is the physical? So as I said in this talk in 2013, we don't know which cells are physically adjacent in the memory controller. This paper says, can we actually figure that out? And we figured that out mostly. And then there's more that I'm not going to talk about, but you can see that this work actually keeps on moving forward. And I'm not talking about the RowHammer works. Okay, so I'm going to almost stop here soon, but basically you can learn more about this. I think for those of you who've taken computer architecture, we've actually covered this in DRAM refresh. Not the exact story, but we have a lecture on DRAM refresh and data retention. But I will go back to the infrastructure. Basically, enabling infrastructure is really important. It's enabled a lot of this research and a lot of other research in RowHammer that I didn't discuss today, but we discussed last time. And you can see that we keep building the infrastructure. And I think it's really important to continue doing that. And this is the paper that I mentioned. This is the DRAM vendor infrastructure, which is essentially a DDR4 version of SoftMC, which has some other interesting characteristics. So if you're interested, you can actually read it. Or if you're interested in doing research, you can contribute to it. It's also open source. You can find it online, so you can contribute to it even if you're not doing research. Okay, that brings me to the end. Wow, we're right at 18:00. Any questions? Okay, let me take questions. Yes, please, go ahead.
For the same problem that's seen from a different point of view, is it possible, how hard is it to optimize outside of the devices to reduce the discharge and extend it?
Yeah, it's a retention time. Very hard. This is yeah, it's very optimized, and it's very hard to control some of these effects, because capacitor it's not like a transistor, but even transistor there's leakage effects that you cannot control, and especially as you reduce the size of the cell, there's a lot more noise that happens, and it's very hard to control. Yeah. I mean, you can use classical redundancy techniques like store one bit in multiple cells, but that's very expensive. Yes.
The retention time problem you mentioned. At RESH, in the first place, memory architectures instead of using capacitors to store charge or to like data bits for charge capacitor. And do you think that, I mean, there are also some types of memory architectures which do not require a genetic feedback. Do you think that's moving away from memory architectures that do require such kind of research because of capacitors? And is a viable approach to get rid of both those retention time problems?
Potentially, if you can do it. So I mean, certainly that's the promise of these resistive memory technologies, right? Like phase change memory. They don't rely on charge to store data. I would say it's really the retention time problems happen, especially in technologies that rely on charge for data storage. Capacitor is an extreme case, but flash memory, for example, has retention time issues as well, even though it doesn't rely on capacitor. It relies on floating gate transistors, for example. But those things also cannot retain charge for very long, especially when you have written to cell for many times. So retention time problems exist on charge-based memories, but with resistance-based memories, for example, they don't exist as much. So yes, that's what we also proposed in some of the other papers that we wrote in 2009, for example. Why don't we use phase change memory to replace DRAM? You get rid of the refresh problem. But unfortunately, there are other issues in those technologies. And there are some retention time effects also. It's not as bad as in DRAM, at least in the technology nodes that we're looking at. So for example, phase change memory has the resistance drift problem. The resistance kind of drifts from one value to a lower value. It's kind of like losing charge, but the resistance is drifting. Yeah. But the time scales are much larger than DRAM. But yeah, that's the promise of some emerging memory technologies. They can get rid of some of the scaling issues that these existing memory technologies are facing. The downside is, like, we first wrote the paper on that topic in 2009, but there was research going on that topic even earlier. So it's been 20 years and DRAM is very strong. So there's no technology that has unfortunately gotten close to replacing DRAM yet. This doesn't mean that research should not be looking at it. Research should be looking at it, but that's a very tough hill to climb. Another question? You have another one, I think. Yeah.
And also part about some like geological demonstration memory architectures where data can be stored with large but in a certain kind of measure.
Certain what matter?
I don't know how actually like it might be called biological memories.
Okay, like DNA storage, like
yeah.
Okay. Okay. Okay.
Are there actually many research going on in this field?
Yeah, I mean, certainly. I mean, yeah, at the ETH physics department, there are people looking at DNA storage actually, and they're also an architecture community. Those are usually targeted as archival storage, meaning not for DRAM. So they're, in my opinion, they're never going to be able to replace DRAM. Never is a very strong word, but there is a fundamental reason, I think, because those DNA storage, for example, it's a very slow reading process. Reading process is essentially very similar to what we have discussed in the genome analysis lecture. You basically read the DNA and figure out what the data is that you encoded over there. And that takes a long time, as you can see. But people are really looking at it from a more archival storage perspective. Can we store data for, I don't know, hundreds of years? And there, I think that maybe there may be some applicability. But the read and write times are, and also error rates, are quite, let's say, not so good compared to DRAM or SSDs. today. There's also other, I mean, it's really good to look at memory technology, I think, memory and storage, I should say. People are looking at actually storing data in glass. There's work at Microsoft Research in Cambridge. And that I think I find that a little bit more promising. And let's say potentially shorter term than DNA storage. So you can check that out. The downside is I think they don't get close to DRAM. If your goal is to really make fast, energy efficient memory, they're not, at least in the current form, they're not there. Right? They don't even get close to SSDs in many cases. Yeah, that's the sad state of affairs. But the good state of affairs, I think it's good to look at these things and see where they can be applicable. Any other questions? Okay, we should probably call the day then. You had a question or no? Okay. Okay, let's.